And I think I will give the midterm results on Wednesday. Um, uh, I almost finished the grading. Uh, Almost around 70%. I already grade the score. I think most of you did well for the midterm, and I hope for the next exam and quizzes, it will be uh, at least something similar to your midterm. Okay, let's start the course. I will review a little bit about the space curves. Okay, so the space curves is basically a curve that is in space in 3 dimensions. Okay, and we will have a parametric equations. Okay, so instead of 2-dimension parametric, we have now 3 x, y, and z, and all those 3 are parametric, in which the parameter is t, the variable t. So if we have a random curve like this, okay, in a space, you have 3 components, functions f, g, and h, in which all of these functions are x, y, and z. Okay, and usually what we write in terms of vector function is usually r equal x parametric, y, and z. Okay, usually like this, or in a basis standards using I, j, and k. That's the vector function. Okay, and basically what vector functions means is it will show you every at every t, every positions that the vectors will be. Okay, so maybe here, here, maybe at t equal maybe -1, or maybe t equals 0, t equal 1, t equal 2, it will be moving out, tracing this curve. Okay, tracing this curve. Okay, so c is traced out by the tip of the vector position of the vector r. And this is example. Another example that probably you can think is if you have the vector functions. Okay, so you have cosine t in x axis, sine t in a j or y axis, and t in k. Okay, so if you remember, in original parametric equations, the 2-dimensional parametric, you have cosine and sine, and you can exchange to the circle, right? The circle equations. Okay, so if you are squaring this, cos squared, sine squared, it's like x squared plus y squared is equal 1, right? So it's like a circle. So in 2 dimensions, or in xy plane, if you see this x and y, it will be making a circle, right? But in the third axis, the z, it will change with t. Okay? So as the circle increase in level in z, the curve will follow along the circular line, but it will move out with the level of this t, okay, with the z. If we are writing this as parametric, we have as This is the parametric. And remember that if I'm drawing in terms of squared like this, and we add all, so we have a circle with radius 1. Okay. So this is a circle, or in 3 dimensions, we call this a circular cylinder or cylinder. So let's draw this. Okay. Now, because we have cosine, sine, and then we have t, we need to decide some number of t. Okay. And because we include cosine and sine, we need to try some t. And to try some t, you can use the trigonometric value. So maybe we can try from 0, maybe pi/2, and maybe pi, 3/2 pi. Okay, and then check with the parametric equations. Okay, and you can check others. So let me draw a circular like this in xy plane. So this is my z, this is x, this is y. Okay, let's start from t equals 0. So when t equals 0, cosine 0 is 1, sine 0 is, or let me just write in terms of x. X is 1, y is 0, t is 0. So 1, 0, 0. So probably here is the 1, 0, 0, because that's the maximum of the radius of the circle. So let me draw this as 1, 0, 0. And then try the t equal pi/2. Cosine becomes 0, and sine become 1, and t is just pi/2. And now to help sketching the cylinder, let's just make a line here for creating a cylinder for the x squared plus y squared equal 1, like we did in the previous chapters. Maybe until here. Okay, now y is 1, so y is around here, and x is 0, and then t is pi/2. So we have maybe around here. So this is 0, 1, and pi/2. So the curve will trace out this point. It's going there, the arrow. And then it will, so if you try another t with the other angle, it will be going behind there. And then you have the circular movement like that. Okay. Now the figure here, or the curve is called, this is a helix curve. So as t increase, the curve take a spirals and going upwards. And the helix is, or the spiral curve, we may see in the, if you imagine this like a spring, okay? Or if you have another helix, it will be like a DNA structure, right? So a helix is a structure that in natures and in other physics phenomena, it's already a common structure. Okay, that's the example for the helix. Now another example. So find a vector. Find a vector function that represents the curve of intersection of the cylinder, same cylinder x squared plus y squared equal 1, and plane y plus z equal 2. So the question is asking a vector function that is in the intersection of the cylinder x squared plus y squared equal 1, the cylinder, and you have the plane. It's slicing the cylinder, and you need to imagine the intersection in between of the cylinder and the plane. Okay. Okay, probably that is the cylinder. And y plus z equal 2 is, let me draw, that is on, this is z, this is y, and this will be the intersections, right? If you draw in 2 dimensions. So this is z, this is y, this is the line, right? And or probably from here to here, because this is 1, this is 2. Yeah. So this line is cutting the the cylinder. Okay, so y plus z equal to, the plane will be in this line. Okay, let me draw the line. And it will be cutting like that. Okay. Now what will happen when you are cutting this cylinder? Like you have like from this angle like this one. Okay. So how to imagine that? Um, Maybe imagine any circular circular shape. Maybe like a sausage. You cut the sausage. Imagine you have. Let me draw here that you can maybe think like clearly. So this is sausage. Okay. And what the shape, it's cutting like this. Okay. So imagine the intersection in between. What kind of uh, shape it will have? The intersection will be like this, right? An ellipse, right? An ellipse. So if you cut the sausage and you have something like an ellipse, not a circle, right? So something similar here that you will have you have an ellipse structure. So maybe it will be oh wait, wrong. Should be this one. Yeah, probably like that. Okay, so you will have something like this. Okay, and this is the one that we are looking for. This is the curve, the intersection curve. So first, we have the x squared plus y squared equal 1, in which we already discussed what it is. So um, the parametric x will be the cosine t, y is sine t. And z is from the plane y plus z equal to. So z is 2 minus y. 2 minus y, and y is our sine t. So z is 2 minus sine t. And all with the t from 0 to, let's say, 2 pi, because it's circular like a circle, right? So we restrict the angle until 2 pi. So the corresponding for the vector is this called parametrization of curve C. There are several examples that we can see and follow, but I don't think we have time to explain all and study all. So I hope you read some intro for the vector functions, but the basic concept is still the same. What you need to do is you need to find the parameter, okay, the parametric equation of each three axis, and then you can imagine how the drawing looks like, and basically that's it. Okay. Okay, this is all the intro for uh, vector functions and space curves. And if you have find some graphing calculator, you can also try to make uh, a vector functions out of that calculator. There will be some interesting graphs like like a toroidal spiral. It's something like this. Yeah. So it has a circular movement, but its movement itself. It's creating a circular. So it's called a toroidal spiral. But I think we can skip that and just go to 13.2, the next section of the chapter. So 13.2, this is derivatives and integrals of vector function. Okay, in the vector functions, let me just write the definitions for the integral. It's similar to what we have learned in calculus 1. We include limit. Okay. Okay, so it's really similar. So we have a limit as h approaching 0. H is a gap. Okay, remember, from the point that we are going to observe to some point that that has increasing. Okay. Usually we did the x, right? Not t. This is x. Okay. So h is a the displacement, the gap. And it's similar, just changing with the t, and this is the first derivative of r. And don't forget that this is true if the limit provided exists. And how uh, the figure looks like. And try to draw. Let's say this is the curve C. This is the vector R. And this is the vector t plus h. And this will be the difference in between. So this will be r t plus h minus r t. So we have the vector pq. This we call the secant factor is the r t plus h minus r t. Okay. Now, based on our knowledge on calculus 1, so you have this, right? So uh, as the limit, okay, of h approaching 0, so meaning the 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 q is getting closer to p, right? It's getting closer to p based on what we write above. So as the limit of h approaching 0, so this will be getting closer to p, and eventually the tangent line, as the definition in the figure will be around here. Okay. So it's like in the 2-dimension. If you have this, you have 2 points that in comparison. So maybe here and here. It's too big, but let's say here, maybe here. So it's H there. So it's getting closer from. Imagine this, if this is P here on the left and Q on the right. So the Q is getting closer to P, in which we can have, let me give you, so if this is the gradient here, gradient, so the gradient is changing, right? So at this P, the gradient is maybe like that, okay? And similar with here, we will have a tangent line at point P that will be looking like this. Okay, as the H is getting closer to 0. But the good news is, this means that everything that we learn in Calculus 1, we're just doing it the same way as it is in this chapter 13. Okay, so the conclusion is just differentiate each component of R. Okay. And here the R prime is defined as, so R prime defined as the tangent vector to the curve defined by R at point P. Okay. Because tangent depends on point. Okay, depends on point. Just remember. We can also say the tangent line to C at point P is defined to be the line through P parallel to tangent vector. You can also write like that one. So meaning you can make a parallel line parallel to the tangent vector dr prime. Okay. Okay, so if the R is, let me just write this, F, G, and H. So all these three is differentiable. Differentiable. Then just differentiate all the components. Okay. So, and I don't think I need to write the proof because I think it's just writing the same limit as before, but in each component, and meaning all the F, G, H, you need to write the uh, the let's say the increasing gap is becoming a delta t instead of h. So let me just write some parts of the proof. Okay. So limit of okay, from here we just divide into three components. So from R we divide to F, and then to G, and then to H. And sorry, this should be that. And minus the F, G, and H at T. Okay, from here, you will notice that every F, G, H, all this, it will be having the same formula as before, and with that in that way we are proving that this is actually just differentiating each component. So we can write this as okay, all will be F prime, G prime T, and H prime T, right? based on what we defined before. Yeah. Okay, and there are terms that is usually we are using in this part is the unit vector. Okay, we have learned the unit vector in chapter 12, but here because we learn and apply in calculus in a tangent line, so we have a unit tangent vector. The definition is still the same as we learned in chapter 12, but the unit tangent, uh, we are using the symbol T, the big T usually. And this is the R prime defined by its value. Same definition as chapter 12, but we are using the R prime for the tangent. Let me give you a few basic example to find the derivative and the unit tangent vector. Let me give you here. Oh, any question before? Any questions? So basically, in summary, all the calculus 1 methods in chapter 13, we are going to use all. The difference is we are just changing it to a vector. We change to a vector. So let's say example 1. So we have vector functions. Okay, so the first typical question in the chapter 13 is finding derivative, finding unit tangent vector. So to find the derivative, we just differentiate each component. Okay, so basically, we differentiate each part. So the first is the x. And if you want to be careful, maybe you can divide into three. If you feel uh, the factors seems too long, if you write in a one line, you can divide into three parametric equations, and later you can combine into one factors. Okay, I hope you are not forgetting how to differentiate this. Okay, so this is using product rule. Okay, I hope you still remember. So I will directly write 1 minus t and e minus t j, and plus 2 cosine 2t k. Okay, because a few of you in the quiz or exam, when you derive, sometimes you're forgetting the product rule and the chain rule. Okay, now to find the, so this is A. To find the unit tangent vector, let me write unit tangent vector is r prime t, which means we need to check the t equals 0. So check t equals 0. So this will be j plus 2k, right? If you put 0 into the equations. Now we can use it for unit tangent vectors. So j plus 2k, and this will be 1 plus 4. So we have 1 over square root of 5k plus 2, and then k. And this will be the unit tangent vector. Okay. And if let's say the similar to the real valued function, the second derivative of r, let's say r t, is the derivative of r prime, which means we can write the second derivative as r prime and then prime, okay, or it's d dt dr dt. There are a few examples. You check your book, you can check, but I think I will skip that for now. We just go to the next one, the differentiation rules, and some theorem, and the integrals. And I think we can finish all now today. Oh wait. Okay. So differentiation rules. Okay. Basically similar with the calculus one. I'm just adding the factors. Suppose u and v differentiable vector function. C is scalar and f is a real valued function. And you can also do the dot product in terms in the derivative. And the result is the product rule. Also, you can cross the factor. And you also have the product rule. And then the last part is the chain rule. Okay. I think it's similar to calculus 1, but just to add some notes for the dot product and the cross product. Okay. The others is I think the same. Um, how we are using the product rule, the chain rule, when we add, when we multiply with scalar, all the same. Okay. Now, if we look at the dot product, um, you will see that we are kind of combine the product rule and the dot product. So what is really happen is, because dot product is just adding the multiply results, right? So if we look at the, so if you let the let's say the vector u, let's say it's all f1, f2, and f3, and v is g, 1, 2, 3. So if we dot this two, we will have f1 g1 plus the f2 g2 and f3 g3. Okay. Now we can write this, all these terms, into sum notations, okay, because it's additional, right? It's additional with the plus. So we can write in a sigma, in a sum. To simplify our notations and to prove the derivatives. Okay, so this is the dot product. So when you are finding the first derivative from this dot product, you are finding the first derivative from the sigma here, from the sum. And this basically, we can move out the sum and just differentiate the inside. So we can have the product rule inside the sum. So that's why the results at the end is u prime t dot pt plus ut. Okay. I think the point that I want to make is because dot product is just additional, it's just making an additional plus, 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 right? So what does it mean is because we derive FG, right? In a sense of a product rule. So we just derive the FG and then the rest is just a dot product, right? So what we are doing is we are using product rule inside a dot product, okay? And that's why we have the conclusions here. This u dot v becomes u prime dot v and u dot v prime. And then similarly with the cross product, we will have the same pattern. So we will have the product rule and then it's crossing each factors, okay? And the rest is actually the same as calculus one, like the chain rule, okay, this one, the product rule, if we multiply with scalar and so on. So this is chain rule, the last one. Okay, that's the some set of rules in differentiation on factor function. Okay, any questions? Oh, this is not a minus. It is arrow. Maybe some of you may confuse that. Okay, I will continue a little bit. I think I can finish the 13.2 today. So because chapter 13 is actually quite short, so it's only three or four sections, and I will just focus on three sections because the fourth one is basically physics, motions, particles. Yeah. So the next thing is the theorem. First, the theorem. Theorem for the, so if okay, the first theorem is if the magnitude of the vector functions is a constant, then the r prime is orthogonal to the vector function. Okay. Okay. Remember that the dot product, we have the if the dot product is 0, then it will be 90 degree in the angle theta, right? So remember the cos right? So if theta is pi/2, that's mean the product is 0, right? Now, because it's a constant, so if I write the dot product of R, so R dot R is basically we are getting this squared like that. And if this is C squared, right? And this is a constant, then if we derive this will be R prime. Or this is just this because it's similar. We can write this in terms of R prime and R, which is equal to 0 because it's equal constant. And we differentiate the constant becomes 0, right? So we conclude that R prime dot R is 0. And from here, we say R prime is orthogonal to R. Geometrically, we can also, using a sphere, to imagine the line. So if a curve lies on a sphere with the center of origin, so this is origin, and so see the spiral like that. So if you have the spiral, and if the R is here, the R prime is always be here. Which means in every point at this sphere, the vector function is always orthogonal to its tangent vector, right? In every point. So if you imagine it's, if you rotate, it will be orthogonal in every point. Okay. So tangent vector. Okay, we can continue to integrals. It's just a little bit. So, and the integral is also similar to what we have done before. We just change the form into a vector. Okay. Okay. Any questions? Maybe before we go to integrals, maybe some example for you. So for the curve, okay, we have the curve is only having two components, x and y. So that means we just need to sketch xy plane. So when t is 0, there's only y value, right? 2, and the x value is 0. And when t is 2, y will become 0, and the x-axis will become square root of 2, and you will have the curve, right? It's only xy like that, just usual xy. This is 2, maybe this is 1, maybe here. Yeah, maybe like that. maybe this is the vector R1, like that. And this will be 1, 1. The tangent vector should be here. Okay, just sketching the curve. And find the R prime. And just differentiate from the curve, from the vector. And then minus J. And plug in 1, we will have this equations. And to help you draw the curve, you can also eliminate the parameter. And it will be more clear, the curve for the xy. Okay, maybe another example. Find parametric equation for the tangent line to the helix. And the parameter is at 0.01 pi over 2, which means we need to equal t equal pi over 2. So find parametric equation for the tangent line. So we need to find the tangent line to the helix at some point. Okay. So first, we can write down the vector. It's 2 cosine t, sine t, and t. First, if you read any tangent, like in the calculus 1, similar to calculus 1, we just differentiate. Okay, we just differentiate. So we differentiate r. So negative 2 sine, and then cos t and 1. And the parametric value for this point is t equal pi over 2, right? So we just use that pi over 2 inside the equations. So we will have -2, 0, and 1. So tangent line through is the line through this point. Through and parallel to vector, this vector. Okay, remember how to find the line. So x. Okay, so I will add the, because x0 is 0, right? So -2t, and y is just 1 because it's plus 0, right? Plus 0. And z will be pi over 2 plus t, right? And this is the parametric equation. So we already done this is the chapter 12, okay? Chapter 12, 12.5. Okay. So most of the chapter 12 will be also applying in chapter 13. So 12 and 13, it has a lot of connections to the, because of the factors. Okay. And if you imagine the curve, if this is a spiral, so the curve maybe around here. If this is 1, 0, 0, maybe here, the tangent vector. Okay, now let's move to integrals. Okay, any questions? No? Let's move to integrals. So basically, if you maybe need some review for calculus 1, you need to check your notes previously, because most of the problems is the same problem in calculus 1, but we change the perspectives. So the next thing is the integrals of vector function. So basically, if we have integral, the definite from a to b of our vector functions, this is by definition is we can use the similar to Riemann sum. So we cut the rectangle, right? But now we imagine in the three components of F, G, and H. So based on this definitions here, what we did is just integrate each component. Same thing as the first derivative. You can have each having a bracket there. If you want to make a bracket. So we can evaluate the integrals by integrating each component. And then from here, we can also use the fundamental theorem of calculus. Where the R, the capital R is antiderivative of R, and so this And that's the 13.2. Okay, so derivative and integral in vector function. So next, I think next Wednesday, I will continue the 13.3, the arc length and curvature. It's actually quite a lot, the last one. So I think if not finished, maybe continue on Wednesday and Monday, and maybe on Monday we can start the chapter 14. But because we already finished 12 and 13, so we need to prepare another quiz. Okay. Another quiz, but maybe next 2 weeks. Okay, next 2 weeks or next 3 weeks. Okay. I will let you know. Maybe we can discuss in maybe next Wednesday. We can discuss. Okay. So I think I will finish up until here, and we will continue on Wednesday. If you have any question, you can ask.